In the paper, From Feature Importance to Natural Language Explanations Using LLMs with RAG, Sule, Tekkesinoglu and Lars Kunze introduce a novel method for generating natural language explanations for machine learning models' predictions. This approach leverages large language models, LLMs, and the RAG algorithm to translate feature importance scores into human-readable explanations. The authors emphasize the importance of model interpretability, particularly in high-stakes applications where transparency is crucial. They highlight the limitations of current methods for generating explanations, such as LLM and SHAP, which often rely on approximations or simplifications that can lead to inaccurate or misleading explanations. To address these limitations, the authors propose a new method that utilizes LLMs to generate natural language explanations directly from feature importance scores. This approach is based on the idea that LLMs can learn to map complex numerical data into coherent and meaningful text. By using pre-trained LLMs and fine-tuning them on a dataset of feature importance scores and corresponding explanations, the authors demonstrate that it is possible to generate high-quality explanations for a wide range of machine learning models. The RAG algorithm plays a key role in this process, as it allows the authors to efficiently search through the vast space of possible explanations generated by the LLM. RAG is a reinforcement learning-based method that uses a reward function to guide the search towards high-quality explanations. The reward function is designed to encourage explanations that are both accurate and easy to understand, as measured by various metrics such as fluency, relevance, and faithfulness to the original model predictions. The authors evaluate their approach on several benchmark datasets and compare the results to existing methods for generating explanations. They find that their approach consistently outperforms other methods in terms of both the quality and the diversity of the generated explanations. Furthermore, they demonstrate that their approach can be applied to a wide range of machine learning models, including linear models, decision trees, and neural networks. In conclusion, the paper presents a significant advancement in the field of model interpretability, offering a new approach that leverages the power of LLMs and reinforcement learning to generate high-quality natural language explanations for machine learning models. This work has the potential to greatly improve the transparency and accountability of AI systems in various domains, from healthcare to finance and beyond. The paper explores the integration of post-hoc explainability approaches with large language models, LLMs, for traceable question answering. It highlights the challenge of object hallucinations in LLMs, which can lead to plausible yet incorrect outputs. To address this issue, the authors propose a traceable question answering method that utilizes an external knowledge source to inform LLM responses. This approach aims to ensure that the LLM acts as a reasoning engine rather than a source of information. The proposed method incorporates elements from social science research on human explanations into the system prompt, guiding the response generation process. The authors present their vision for creating this integrated approach, outlining each component and illustrating its viability through a real-world dataset. This integration has the potential to bridge the gap between complex model outputs and user comprehension, advancing the development of human-understandable explanations. The paper also provides a brief overview of recent advances in image explanations, including intrinsic and post-hoc explainability methods. Gradient-based techniques, which analyze the gradients of the model's output with respect to its input features, have been extensively studied. However, these methods may not provide intuitive explanations for non-technical users. The author's proposed approach aims to address this limitation by leveraging LLMs as a means of generating more accessible and transparent explanations. In the realm of explainable AI, researchers have been exploring various approaches to enhance model interpretability. One such approach involves employing attention mechanisms, which assign weights to different parts of the input data based on their relevance to the model's decision. However, these mechanisms may lack explicit interpretability, leading to efforts to integrate them with natural language processing. Long short-term memory encoders have been used to extract features from video clips, with LSTM decoders generating descriptive texts based on these features. While effective in image captioning, these methods provide textual descriptions rather than visual explanations. Perturbation-based approaches, a model-agnostic method that perturbs input data and observes changes in model predictions, have also been proposed. Building on this research, the authors integrate semantic perturbation analysis with pre-trained language models, translating the results into the text modality for enhanced explainability. Recent advances in large language models have marked a transformative era in NLP research. These models have become pervasive across diverse applications and have recently gained attention as post hoc explainers, highlighting their potential to elucidate the decisions made by other predictive models. However, a persistent challenge for these models is the occurrence of object hallucinations, which raises questions about the faithfulness of explanations to the underlying model. To address this issue, the authors recognize the role of the semantic map layer in capturing the meaning and context of the physical surroundings. By effectively encoding valuable semantic information into LLMs, they can truthfully represent and comprehend the intricate details of the model output within the language space. In the context of XAI, the audience for explanations is predominantly human. Thus, understanding what makes an explanation human-friendly is paramount. According to Miller, current work on interpretability in machine learning relies solely on researchers' intuition regarding what constitutes an appropriate explanation for humans. Miller's survey highlights 4 major characteristics of explanations drawn from findings in social science research on human explanation. Explanations are social, causal, selective, and contrastive. The authors briefly discuss these characteristics in relation to XAI before demonstrating how they integrate them into their application. Explanations are fundamentally social, involving an interactive exchange between the explainer and the explainee. This exchange is governed by certain rules, such as Grice's conversational maxims, which include principles of quality, quantity, relation, and manner. Moreover, incorporating anthropomorphic traits like politeness markers, warm tones, and empathetic expressions can enhance the effectiveness of human interaction. Theory of mind also plays a crucial role in social explanations, enabling agents to tailor explanations based on past interactions and evolving contexts. Causal explanations aim to elucidate the cause and effect relationship underlying a decision. In machine learning, identifying the most influential features can provide insight into key causal connections to the prediction. This process, known as causal inference, involves counterfactuals and abductive reasoning. Counterfactuals involve using a model of hypothetical cases to derive an explanation, while abductive reasoning infers causes from observations to form the most probable explanation. Explanations are contextual and selected based on various criteria called causal selection. The explainer selects a subset of causes relevant to the context, as the recipient of the explanation typically cares about only a specific subset. Hilton argues that explanation selection is used for cognitive reasons since causal chains are often too large to process. In the realm of machine learning interpretability, understanding human explanation selection criteria is paramount. People tend to choose explanations based on abnormality, relevance, and simplicity. In machine learning, identifying abnormal events corresponds to deviant or higher feature importance values. Explanations are also contrastive, as individuals are interested in the factors that need to change for a prediction to change. The authors propose a traceable question-answering methodology, which includes an explainability approach for extracting feature importance and a prompting technique to generate accurate and human-friendly explanations. They employ subtractive counterfactual reasoning as an XAI technique, quantifying the variation in model output through systematic modifications of input components. This approach is exemplified by occlusion analysis and feature importance attribution. The paper provides an application example illustrating how to establish a connection between the model output, the explainability technique, and language models to produce natural language explanations in an interactive format. This methodology aims to bridge the gap between complex machine learning models and human understanding, providing insights into the decision-making process of these models. This study introduces a decomposition-based approach to analyze output variations by decomposing input values. It measures these variations to determine the impact degree on an outcome and reasons about the importance of each feature value. The model assigns a class label and prediction probability given input y. To measure the effect of each input value, we observe the model's prediction p for y without the knowledge of event t equals tk, where tk is the value of feature t. This yields an array containing probabilities for all perturbations resulting from decomposition. To determine the importance of an individual feature T, we identify the max and min values within this array, establishing the decision boundaries for the given input. Next, we compute the feature importance as the position of the probability after decomposing the feature relative to the max and min probabilities. This computation is expressed as follows. Importance, T, equals P, x, ytk, max P, x, ytk, P, x, ytk, max P, x, ytk, minimum. This approximates an importance value between 0 and 1 for each input feature. To enhance comprehensibility, these values are rounded to the nearest integer. This analysis is also conducted for the categories following the main prediction simultaneously to generate explanations for the contrastive cases. The study further integrates external knowledge sources to provide responses to user inquiries through a process known as retrieval augmented generation, RAG. This method improves the performance of LLMs by referencing an external knowledge source prior to generating a response. The proposed system aims to provide transparent and interpretable question-answering capabilities by leveraging a knowledge repository to generate explanations for user queries. To achieve this, a system prompt is designed to guide the language model in producing consistent and predictable responses. The prompt includes a single-shot example, potential user inquiries, and instructions on how to address them, as illustrated in Figure 3. The approach is demonstrated through a visual scene understanding task, specifically scene classification, which involves categorizing images based on their content and inferring high-level semantic scenes from low-level visual features. This task has critical applications in human-robot collaboration, autonomous driving, and other autonomous physical systems that rely on semantic segmentation to inform decision-making processes. The Google NetPlaces 365 model, trained on the Places 365 dataset, is utilized for scene recognition and classification tasks. The model is applied to the CamVid dataset, which contains manual annotations across 32 classes, including elements such as buildings, driveways, and pedestrians. The DeepLab v3 Plus deep learning model is trained on the CamVid dataset for semantic segmentation, and the results are presented in Figure 2. The emphasis of this work is not on the performance of the off-the-shelf models used, but rather on the decomposition-based explanation approach. Semantic information plays a crucial role in autonomous vehicle decision-making processes, as it captures the meaning and context of the physical surroundings observed in the road scene. This includes understanding the appearance of various elements such as buildings, driveways, and pedestrians. The proposed approach leverages semantic features from the DeepLab v3 Plus model to provide visual explanations for the scene classification results. Figure 2 shows the segmentation result for an example scene, where feature importance values below a certain threshold are grayed out. The visual explanation for the scene, parking lot, is presented, highlighting the critical role of semantic information in autonomous vehicle decision-making processes. The use of off-the-shelf models allows for the focus to be on the explanation approach, rather than the performance of the models themselves. The proposed system prompt and decomposition-based explanation approach provide a foundation for transparent and interpretable question-answering capabilities, with applications in various domains that rely on semantic segmentation and scene understanding. In the realm of autonomous vehicle systems, this research aims to enhance user understanding through the application of semantic segmentation. This process involves identifying and categorizing elements within an image, such as cars, pedestrians, and roads, to provide a nuanced comprehension of the environment. By leveraging this information, the system can generate insightful explanations for its decision-making processes, which could be beneficial in post-incident forensic analysis. The study utilizes a knowledge source containing information about the model's output and other observations, as shown in Table 1. This table highlights the prediction of a parking lot with a 52% probability, along with feature importance and the effective removal for each feature. A contrastive case involving an industrial area is also presented, demonstrating the model's ability to differentiate between various scenarios. Figure 4 illustrates the dialogue generated from this data, showcasing the balance between being informative, supportive, and engaging. The responses justify the model's output by emphasizing its most significant features and delve into contrastive explanations by detailing lower likelihood classes. The evaluation results are presented in this section, where 9 distinct scene classes were analyzed across different scenarios. The responses generated by GPT 3.5 and GPT 4 models were assessed in terms of sociability, causality, selectiveness, and contrastiveness. This research aims to improve user understanding and trust in autonomous vehicle systems through enhanced explanation capabilities. The paper presents an AI model for autonomous driving, capable of adapting to various scenarios and providing concise explanations. This model is equipped with details such as predicted class, alternative predictions, probabilities, feature importance, and how certain factors affect predictions. In a given example, the AI model identifies a residential neighborhood with a 40% probability, highlighting features like driveways, sidewalks, trees, and cars as highly influential. It also explains the relevance of these features in driving scenarios. When asked about the absence of a sidewalk, the model predicts a decrease in the probability of being in a residential neighborhood to 20% and an increase in the probability of being on a highway to 13%. This demonstrates the model's understanding of key causal connections and its ability to highlight abnormal values that significantly contribute to predictions. The paper also examines sociability within the responses, focusing on the overall tone and sentiment conveyed. Using the valence-aware dictionary and sentiment reasoner, Vader, it is observed that there is a noticeable positive trendline in the sentiment scores for both models, indicating a prevalent positive sentiment. Overall, this page of the research paper presents a comprehensive overview of the AI model's capabilities in autonomous driving, its understanding of driving scenarios, and its sociability in terms of sentiment. Predictive analytics of driving scenarios reveals the significance of features such as cars, buildings, and poles in determining the likelihood of being in a parking lot versus an industrial area. In a parking lot scenario, the system assigns a probability of 11% to an industrial area, 9% to a motel, and 6% to a gas station as alternative possibilities. The presence of cars, buildings, and poles serves as key indicators for these predictions, with cars exhibiting the highest feature importance in a parking lot scenario. A sentiment analysis of dialogue generated by GPT-4 reveals a general inclination towards positivity, with polite and helpful expressions prevalent throughout the corpus. The analysis of social cues within different phases of dialogue, including opening, clarification, and closing statements, underscores the model's ability to acknowledge its limitations. Notably, instances where the model is unable to retrieve answers from an external knowledge repository are accompanied by expressions of limitation, demonstrating a degree of self-awareness. The predictive model's reliance on visual features such as cars, buildings, and poles highlights the importance of contextual understanding in driving scenarios. The sentiment analysis of GPT-4-generated dialogue, on the other hand, underscores the potential for AI systems to engage in polite and helpful communication. These findings have implications for the development of AI-powered driving assistants and conversational agents, emphasizing the need for contextual understanding and effective communication. The analysis of social cues in GPT 3.5 and GPT 4 dialogue responses reveals a distinct pattern across conversation phases. Opening statements frequently employ greetings and inquiries about the interlocutor's well-being, aligning with conversational maxims. Clarification statements utilize contextually relevant terms, reflecting the model's ability to engage in meaningful exchanges. Closing statements convey sentiments of well-wishing or safety, with a higher frequency value attributed to their brief nature. Qualitative assessment confirms the contextual relevance of these terms, aligning with conversational maxims. Both models occasionally repeat certain phrases, albeit with penalties to discourage repetition and promote diversity. The analysis of part-of-speech pronouns as social interaction markers shows that both models adequately applied pos pronouns, indicating their ability to engage in social interactions through the use of pronouns that establish relationships and roles within the conversation. Overall, the findings suggest that GPT 3.5 and GPT 4 are capable of generating dialogue responses that incorporate social cues effectively, enhancing the conversational experience by making it more natural and engaging. In the context of evaluating the expression of causality in language models, This section focuses on the frequency of causation terms used by GPT-4 and GPT-3.5. The analysis reveals that if is the most frequently used term for both models, often employed for expressing counterfactual reasoning. GPT-4 demonstrates a higher frequency of causality terms and greater diversity in expression compared to GPT-3.5. Qualitative review of grammatical structures indicates two primary patterns suggesting cause-effect relationships within the text. The first structure pertains to how the presence or absence of certain features influences the likelihood of specific scenarios. The second structure involves a cause-effect relationship between feature importance and probability, indicating that features with higher importance scores exert a greater impact on probability. The section also evaluates the selectiveness of the models in detecting unusual values within the provided knowledge repository, inferring potential causes from those observations, and selecting the most relevant ones to construct an explanation. The evaluation encompasses analyzing responses across the number of causes given, graded selection, and sort order to assess whether expected causes are addressed correctly. The number of causes varies across scenarios, with some exhibiting only a single highly important feature greater than 5, while others might involve multiple high-importance features with varying degrees of significance. In a qualitative assessment of responses, GPT-4 outperforms GPT-3.5 in terms of selectivity and simplicity. Table 2 reveals that GPT-4 has a higher success rate of 76% compared to GPT-3.5 feed-s 24% in identifying the most relevant cause. GPT-4 also shows fewer subpar and unfulfilled responses, and it does not reference features not present in the knowledge source as potential causes, unlike GPT-3.5. Table 3 evaluates the responses in terms of simplicity, including metrics such as the frequency of technical jargon, response length, and the number of causes cited. The results indicate that GPT-4 has slightly simpler responses than GPT-3.5, with lower values across all three metrics. This suggests that GPT-4 is more accurate and selective in identifying the most relevant causes from a set of possible causes, while also providing simpler explanations. A comparative analysis of two language models, GPT-3.5 and GPT-4, reveals their capabilities in generating explanations for their outputs. The analysis is based on three metrics: the use of technical jargon, the length of the responses, and the number of causes cited. It is observed that GPT-4 tends to use technical jargon marginally more frequently than GPT-3.5, but generates simpler responses with fewer causes cited. Both models demonstrate an awareness of their limitations when faced with out-of-scope questions. The page also examines the expression of contrastiveness in the model's responses, which is crucial for providing comprehensive explanations. A dictionary of contrastive terms such as distinguish, different, contrast, and compared to is compiled to analyze the occurrence of these terms in the generated responses. The results show that GPT-4 employs a wider array of contrastive terms than GPT-3.5, exploring diverse ways to express contrasts in its explanations. Overall, the findings suggest that while GPT-3.5 tends to adhere to one type of contrastive explanation, GPT-4 is more versatile in its approach. This study introduces a novel approach to post hoc explainability, integrating large language models, LLMs, with decomposition-based explainability techniques. This method promotes transparency and interpretability in scene understanding tasks by combining LLMs with semantic feature importance. It has potential applications across various domains, including critical areas such as medical applications. The study also highlights the importance of contrastive explanations, which can vary significantly in effectiveness. Well-developed contrasting explanations include alternative scenarios with counterfactuals to strengthen the case, while weakly constructed contrastive explanations fail to explore what-if scenarios to elucidate the disparity between two situations under comparison. The paper identifies areas for further exploration and improvement, such as the overuse of social cues by LLMs, which can become vexing over time. It suggests evaluating these interactions through human subject studies to understand user perceptions of the explanations provided by the LLM. Future research could also explore dialogue management strategies to address issues related to interaction and personalization. Additionally, the dynamic nature of the external knowledge source offers the potential for further expansion with additional observations, ensuring that the system remains relevant and up-to-date. Incorporating multimodal elements, such as combining text with visual explanations, can enhance the effectiveness of the responses. The estimation of feature importance values is also subject to perturbations and computational processes, requiring assessment and reconciliation of differences across algorithms to ensure stability and consistency. The study was supported by the Wallenberg AI, Autonomous Systems and Software Program, WASP, funded by the Knut and Alice Wallenberg Foundation. The paper presents a comprehensive review of the current state of explainable artificial intelligence, XAI, in the context of large language models, LLMs, and their applications, particularly in autonomous driving. It emphasizes the importance of transparency and accountability in AI systems, citing various studies that underscore the need for explainability in machine learning models. The authors discuss several key concepts, including the notion of transparency in the EU regulatory framework for AI, the risks and limitations of post-hoc explainability methods, and the challenges associated with interpreting black box models. They also provide an overview of various XAI methods, such as model interpretability, feature importance, and visual explanations, which are crucial for understanding the decision-making processes of complex AI systems. In addition, the paper explores the role of LLMs in autonomous driving, where explainability is critical for ensuring safety and reliability. The authors discuss how LLMs can be used to fuse object-level vector modality for explainable autonomous driving and provide a survey on multimodal large language models for this application. Furthermore, the paper reviews several techniques for visualizing and understanding convolutional networks, such as GradCam, which uses gradient-based localization to generate visual explanations from deep networks. The authors also discuss the importance of neural machine translation and its relevance to XAI, as well as the challenges and limitations of large language models in terms of explainability. Overall, the paper offers a detailed analysis of the current landscape of XAI, highlighting both the opportunities and challenges associated with developing transparent and accountable AI systems. It emphasizes the need for further research in this area to ensure that AI technologies are safe, reliable, and beneficial for society. In the realm of artificial intelligence, particularly conversational agents, explainability is paramount. These agents must provide clear and understandable explanations for their actions and decisions, as well as understand and respond to human emotions and social cues. Drawing on insights from psychology, sociology, and philosophy, a framework for creating more empathetic and transparent conversational agents is proposed. Social attribution and explanation play a crucial role in enhancing user trust and satisfaction with these systems. The paper also reviews various methods for explaining machine learning models, including perturbation-based methods, contrastive explanation, and visual explanations. These approaches aim to provide insights into how models make predictions and decisions, which can help in identifying biases, improving model performance, and enhancing user understanding and trust. Furthermore, the authors discuss the importance of contextual importance in visual explanations for deep neural networks. This involves identifying and highlighting the most relevant features or inputs that contribute to a model's predictions, thereby providing a more nuanced understanding of its decision-making processes. In addition, the paper explores the application of explainable AI in autonomous vehicles, where transparent and accountable decision-making is crucial for safety and public acceptance. A framework for generating explanations for vehicle actions is proposed, which can help in improving system design, enhancing user trust, and addressing regulatory requirements. Overall, the paper emphasizes the significance of explainability and transparency in AI systems, particularly in applications that involve human interaction or critical decision-making. By developing more empathetic and transparent conversational agents, we can foster greater trust and understanding between humans and machines. Recent advancements in deep learning for image and video analysis have led to significant breakthroughs in various domains. Large language models have emerged as crucial components in text generation, with potential applications in autonomous driving, human-robot collaboration, and medical imaging. In autonomous driving, real-time object detection and semantic segmentation techniques are vital for navigation and safety. Techniques such as YOLO and SSD have achieved state-of-the-art performance in object detection, while encoder-decoder architectures with at-rest-separable convolution have shown promising results in semantic image segmentation. In human-robot collaboration, deep and machine learning techniques are being explored for modeling and assessing intelligent systems for safety. Hierarchical vertex regression-based segmentation has been applied to head and neck CT images for radiotherapy planning, highlighting the importance of accurate segmentation in medical imaging. Large-scale image databases like Places, containing millions of images for scene recognition tasks, have also been leveraged for training and evaluating deep learning models. The paper reviews encoder-decoder architectures with at-rest-separable convolution, which have achieved state-of-the-art performance in semantic image segmentation benchmarks. At-rest-separable convolution allows for efficient feature extraction and aggregation, enabling the model to capture contextual information and produce accurate segmentation masks. The authors also provide an overview of semantic segmentation with deep learning, summarizing key concepts, methodologies, and significant findings in this area. The survey highlights the achievements and challenges in deep learning for image and video analysis, emphasizing the need for continued research and innovation in this rapidly evolving field. Future work may focus on addressing limitations such as computational efficiency, robustness to adversarial attacks, and explainability of deep learning models.